This video is produced for the use of all students enrolled in the EPO 322 Diesel Engineering 2 simulation course held at Cal Maritime. This is the first of a two-part video lecture on compressed air and cooling water systems. Reading material for this presentation can be found in Modern Marine Engineer's Manual Volume 2. This is not one of the required tests, so it has been placed in the library under reserve under my name for this course. The lecture objectives are describe the important design features of the following system: start air, control air, ship service, saltwater cooling, low temperature freshwater cooling, high temperature freshwater cooling, and also to discuss the causes and prevention of start air explosions. Also discussion of pump compressor control and automatic standby features. The simulator is based on a large, slow-speed, crosshead type diesel engine. And these engines, as well as most auxiliary engines that are used for generation of power, use direct injection starting air to rotate the engine to a sufficient speed that it'll start. With these large engines, you're talking a very high volume of air, and that air is injected into the cylinder at the proper time so that it will run in the ahead or direct or astern directions, and it would follow the firing order of the engine to simulate the burning of fuel in that cylinder. So the propulsion and auxiliary diesel generators are started by the timed injection of high-pressure compressed air directly into their cylinders. For propulsion engines, regulatory requirements dictate that sufficient air must be stored to start the engine in a minimum of 2 receivers without recharging. All right, so what we're talking about here, redundancy. You can't just have one start air receiver, because if that was become damaged, you have no way to start the engine. So there's a minimum of 2 receivers, and for these big engines, you may see as many as 4 receivers because they are so large. When you're maneuvering for a direct reversing engine, it is a requirement that you have the bottles will store for at least 12 consecutive starts. For a non-reversing engine, it is at least 6 consecutive starts. So when you're talking reversing engines like these big slow speed, when you're maneuvering, each time that you change direction, each time you go from a head to a stern, you're going to have to stop this engine. Also, at dead slow, the minimum speed is typically around 6 knots, which is too fast, say, to approach a dock. So the mates will have to start and stop this engine to control speed of the vessel. So 12 starts is what the regulatory agencies believe is a safe number, so that they will not have a casualty due to their inability to start an engine. Believe me, the captain and the pilot are very conscious of this while they're bringing the ship in and out. But I also want to point out that this 12 consecutive starts, that is based on not having a lot of weight on the vessel. Let's say you're coming into a port and you're doing the pre-test of the emergency systems prior to coming in. One of the requirements there is that you stop and reverse the main engine prior to taking arrival. Well, let's say you're doing 15, 18 knots out in the middle of the ocean. When you shut the fuel off that engine, that vessel has way on. That water is moving along the hull, striking the prop flukes and turning this main engine over. It's going to revolve at a fairly high speed. So to try to stop it, you would have to expend enough air to counter that turning force, stop the propeller, and then turn it into the astern direction. Above 8 knots, you probably will not be able to do that. There is enough force on that propeller that you can easily expend all your start air bottles and not be able to start the engine. So another limitation is that above typically around 8 knots, you cannot reverse. So what the mates will do typically is to try to reduce the speed of the vessel. You'll go hard to port, hard to starboard, and that corkscrewing movement through the water will reduce the speed of the vessel, and then once you're down below 8 knot level, then you can go ahead and start the engine. To allow for a reduction in the size of the receivers, typical storage pressure is between 25 and 30 bar. 30 bar is around 450 psi. This is high pressure air. So high pressure air receivers hold an enormous amount of energy, and extreme caution should be exercised when working on these systems. You don't work on these systems until they're drained of pressure. It is extremely dangerous to work on any fittings, valves, any components of the start air system if there is any chance that they are pressurized. It's best just to drain your start air receivers or make absolutely sure that the line that you're working on is drained prior to any work commencing. You'll typically have between 2 to 4 main start air compressors. The ones that I've typically seen are piston type, though I believe there are now some rotary high pressure air compressors out there. The simulator uses these piston type, and that is what we're going to discuss today. So you may have between 2 to up to about 4 of these main start air compressors, and they use a lot of energy when they run. If the bottles have been discharged, you're talking say 30, maybe 45 minutes to refill these bottles. So that's why monitoring for the mates of these start air bottles is very important, because once they're drained, they take a considerable amount of time to recharge. You'll either have also a smaller, what they call a topping up air compressor, or with the one with the simulator, the emergency air compressor. These are smaller units with a topping up air compressor. That one would be used out at sea, and instead of a main air compressor coming on to bring the bottle up, these little topping air bottles or compressors are there just to keep the bottles full when there's a light load. And we will talk in a minute about the emergency air compressor. So just realize that you're going to have at least of these start air, 2 of these start air bottles, and in the case of big slow speeds, these can be very, very large receivers. This is the Kongsberg system, their start air system, and I want to point out a few things. One is that you have 2 of the compressors. You've got a main compressor here and another here, and then on this we have what they emergency start compressor. The mains, you're bringing in air through the inlet here. These are piston type. They have an interstage air cooler and an aftercooler, and each one of these is protected by a relief valve. One operational aspect that I want to bring up, if you ever walk past an air compressor and this interstage relief valve is lifting, but your output pressure from the compressor is low, you have a problem typically with cooling water to this intercooler. What happens is these inner and after coolers are pulling out the heat of compression, and by reducing the heat contained in the air, it also reduces the volume required to store that air. And typically your first stage cylinder has quite a bit more volume than the second stage cylinder. So without this cooling, that hot air cannot fit into that secondary receiver, the cylinder, and you have lifting of this relief valve. So these compressors are used to fill these 2 main start air bottles, and those start air bottles will supply control air to the pneumatic control system from the main engine, and also the starting air for direct injection. Now, these bottles are quite large, and during normal operation, you would only have one of these bottles lined up for service. Again, you want redundancy. These bottles are huge. There's no reason to have both on the line if you're just starting your ship service diesel generator. So typically, only one will be in service unless you are maneuvering. And during times of maneuvering, then you would have both of these main start air bottles operational. It's important to drain these bottles on a regular basis and not allow oil or water to accumulate within the cylinders. There is also here a bypass of your control air compressor. In other words, if the control air compressor was to fail or have a problem, you can opening this valve, and that goes through a pressure reducer, you can have a control air supply. This is really important that you find this very quickly whenever you walk onto a vessel, because if it happens to you, it'll typically be 2 in the morning, and you need to know where this is to make quick corrections. Another system requirement is to provide an independent means of starting the ship's diesel generators in an emergency. You may have a small emergency receiver that's floating on the starting air main. This emergency receiver can be charged by an air-cooled compressor, which is driven by an electric motor supplied from the emergency switchboard, or a small diesel engine, which can be hand cranked to start. So what we're talking about here is, in an emergency, something has happened, you have no air in your start air receivers, that you would have this small start air receiver, the emergency start air receiver, that can supply air to start up your diesel generators so you can get out of a blackout situation. The Kongsberg is supplied this emergency start air compressor with an air-cooled intercooler that can supply air to this smaller emergency start air receiver. Now, they're also showing this hand pump, which is a little bit a misnomer. This would not be a hand pump. That's not practical. You would have say around a 5 horsepower little diesel engine. So basically think a lawnmower engine that would run a small compressor to fill that bottle if you have no power at all, if there's no power to run that emergency start. These little diesel air compressor would have to be hand cranked. The engine has to be small enough that you can start it up by hand, so you know that you can get that up and running in an emergency. Now, normally, this emergency air compressor is not going to be used. These check valves, you've got 2 check valves on either side tying this into the main start air system. That green arrow is indicating direction of flow. So you have airflow from the main compressor can be used to fill this tank. But this tank can only go to the diesel generators. The green arrow is direction of flow. It cannot flow to the main start air system. All right, this is the virtual view for the Kongsberg. On your left is your emergency air receiver. This receiver in reality would probably be about the size of your ship service air receiver on the Golden Bear. And then beside it is the emergency air compressor, the 2 mains, and then the 2 main start air receivers. By the way, this is too small. Those start air receivers would be probably 5-6 times what is depicted here. But anyway, this is the virtual system as used on the Kongsberg simulator. Now I want to switch over a little bit to start air system explosions. A start air explosion can occur during an engine start sequence, and where oil which has been accumulated within the start air receivers or the interior surfaces of the piping and manifold is ignited by an ignition source. And this ignition source is a flame front coming out of the cylinder typically. So what we're talking about is you have these reciprocating air compressors. They are lubricated by oil. And if that oil was to accumulate in the lines and in the receiver, and you have a flame, you've got plenty of oxygen, If you have a flame coming out of the cylinder and into the interior of the piping, which can happen during a start sequence, then that can ignite and explode. So it's a very limited amount of fuel, only what little bit is accumulated, but if it was to burst a line, it can have very dire consequences. So the source of the ignition can be a leaking air start valve, as the hot gases from the cylinder combustion can leak back into the start air manifold, or fuel leaking into the cylinder when the engine is stopped. When the engine experiences a start sequence, the fuel in the cylinder can auto-ignite and travel back to the manifold through the open start air valve. Auto-ignition of oil deposited on the inner surface of the manifold can occur, though I think it's a little bit less likely. All right, to prevent this flame front from coming out of the cylinder, there's a couple different methodology for protection. One of them is the flame arrestor. Now, the flame arrestor is situated typically between two flanges. It's made out of a fairly thick metal, and it has holes drilled through it. The idea that, kind of like a flame screen on a tank, as that flame goes through that mass, those holes through that piece of steel or bronze, as it goes through that quenches the heat away and snuffs out the active flame. So that's a flame arrestor. You also have, in the case of the Burmeister Wain, like we have on the simulator, you have a bursting disc. Now, a bursting disc is if there is an explosion in the line, that there's a thin metal disc that ruptures, and by rupturing, that releases that pressure to prevent this damage to the system from that explosion. Those bursting discs, though, once this has occurred, would have to be replaced prior to the engine being started. To prevent a start air explosion, you want to minimize the oil carryover from the start air compressors. The air start system must be protected by a non-return valve at the starting air supply to the main engine. It is a requirement for diesel engines with a bore size greater than 230 millimeter. For the direct reversing main engine flame arrestors or bursting discs are required for each cylinder fitted between the cylinder start air valve and the manifold. For non-reversing an auxiliary engine, a single flame arrestor or bursting disc is acceptable, fitted at the supply engine inlet to the start air manifold. In addition, a relief valve may be fitted to the manifold where flame arrestors are used instead of bursting discs. Next system we're going to talk about is ship service and control air systems. An important point on this, and the Europeans have blurred this. One of the things I want you to note on the Kongsberg is you do not have a separate service air system and control air system like you have on the Bear. They've combined it, but there is specific differences. Ship service air supplies non-vital systems. Control air supplies critical systems. And today's vessels still use pneumatic controls very heavily, not for the actual controllers themselves, but for control valve. So a loss of control air can mean the blackout of the vessel, that you would lose control of your systems and black the vessel out. So specifically, you have to think about that. And that's why American ships, we typically have them separate, which happens fairly often. You may have the deck crew out on deck chipping and removing rust. It's not unusual, actually, for them to use so much ship service air that they drain it. Now, with a combined system like this, you run the risk of blacking out the vessel because of the fact that they have been chipping out on deck. Where a separate system like on American, they can drain the ship service air system. It's not such a big deal because your control air is separate. So with this European system, you would really have to treat the whole ship service and as a ship service and control, treated as a vital system. Now again, you do have on these a crossover from the ship service, from your start air system. So if you were to lose your control air compressor, then your backup is off of the ship's starting air bottles. But you need to be conscious of that, because if this was to happen to you and you get alarm for low ship service air pressure, you need to immediately be opening that valve to make sure that you do not lose control on vessel systems and have a blackout. On this too, you do have a filter dryer, and they're showing it on the general control airline. Typically today, by the way, you will have this both on the ship service and control air. Automatic drain traps are to be fitted at receivers and moisture separators. You got to make sure you drain the water out of these systems and keep them drained. But a lot of times today that's automatic, but automatic systems fail, so you do want to make sure that you keep an eye on it. The pressure in the receiver is controlled automatically by starting and stopping of the compressor. And these are done with pressure switches. You have a pressure switch to start the unit up and to stop it. Typically, you also have manual control of the compressor, which will bypass the pressure switches and can be used to test a receiver safety valve. In other words, you've got the Coast Guard coming on, and they will test on occasion what is the popping pressure of your safety valves. Local control, you can typically switch it to manual and start the compressor and raise the pressure up in the cylinder until the valve relieves. This could also be used if you had a problem with your control switches, but in this case, you would have to stand there all the time and switch it on and off. Again, this is not showing a filter dryer to your ship service system. Most ships will have this today because it is very disadvantageous to send oil and water and dirt into any pneumatic device. And in fact, on the barrel, you'll notice that our filter dryer on the ship service system is our biggest one. So control air supplies compressed air to vital systems. Vessel automation typically depends on pneumatic control valves for system control. Loss of control air can result in main propulsion shutdown and plant blackouts. Never pipe non-vital air loads to the control air system or vice versa. Pneumatic control devices are very sensitive to damage from water and dirt, and it is critical that sufficient dryers and filters are installed. Refrigerated compressed air dryers are typically used and may be augmented by filter dryers installed at the instrument itself. This slide is a representation of the Kongsberg saltwater system. Saltwater systems in modern design are dictated that the cooling system is minimized to reduce system maintenance. On the old vessels, saltwater systems were probably 35% of our maintenance. So to reduce the amount of maintenance, the saltwater systems now are as small as possible. The reason that there are a lot more maintenance is that cleaning of the heat exchangers and supply lines to remove marine organisms and the replacement of sacrificial anodes to protect the heat exchangers and the lines from galvanic corrosion. So you had a lot of repairs to corrosion and also removal of the marine organisms. You still have that, but now the systems are quite small, so that reduces the amount of maintenance. And I want to think too, the saltwater systems are more expensive because you are using an electrolyte, the salt water, and also that you end up having to put in systems to kill the marine organisms coming in. Also too, the lines and the valves and the pumps have to be made out of a corrosive resistant material, or in the case of a lot of modern ships now, the inside of the piping is all rubber coated. But this all adds to the cost as well as the maintenance. Now, on the system, you have a low C suction and a high C suction. Most vessels, cargo vessels, will only use their low suction. unless you're coming into a port that has a muddy bottom and you don't have a lot of draft underneath the vessel. In that case, they would switch to the high suction. You have a low sea suction and a high suction. Most cargo vessels normally remain on the low sea suction unless they're coming into port with a muddy bottom and not a lot of water underneath the hull where they're afraid that they would suck up mud into the system. Then they would go to the high. But this is a ultra-large crude carrier. In the simulator, the depiction. So one of the aspects of this is that when that cargo is loaded or the cargo has been discharged, the vessel draft changes dramatically. It can change as much as on one of these really large modern ships, modern tankers, as much as, say, 20 meters, 60 feet. So typically, when the vessel is unloaded, it's going to sit much higher in the water, and that high suction will be out of the water. Then the other problem is when you are fully loaded, then that sea suction is very deep in the water, and that changes the pressure dramatically. So most tankers will switch from a low sea suction to a high sea suction, really dependent on their loading condition. So just realize that. And then on the Kongsberg, you can actually see the green around the hull. That is the depiction of the saltwater level outside the hull. And so that you realize that if you were to switch over to the high suction, that you would actually draw in air instead of water. Okay, so this is your low suction, and this is your strainer. You have 3 pumps. 2 large pumps, your main saltwater pumps, which are driven or powered from the main switchboard, and a much smaller auxiliary or harbor pump that is driven off the emergency. The output of this goes to 2 big freshwater coolers. Only one of these coolers would be in service at any time, and these will change saltwater on one side, fresh water on the other. So that fresh water, which is using treated distilled water, is what is cooling most of the components on the ship. Then you have a condenser, and this is showing it more like a standard heat exchanger, but this would be a steam condenser off of your steam turbine generator. And then these 2 are going to some coolers in the diesel generator room. And they're showing them each generator has its own supply. This is for your evaporator. This is for your air conditioning. And then it goes over the side. This setup also has a 3-way valve and a temperature control. And this temperature control is to allow water to recirculate back to the suction of the pump instead of going over the side. And this is set up specifically for Arctic operations. In that, one of the things that can happen in very, very cold waters, ice can form across the sea chest and then block off flow into the system. By maintaining or by recirculating this water back to the pump and maintaining it above 20 C, you're taking less water out of the sea chest, and it's less likelihood that it will freeze up. You also have on here your fire and general service pumps and an emergency bilge suction. That emergency suction would only be used in a flooding condition. In other words, you've had a casualty and the engine room is flooding. You can open that valve in an emergency to remove so that you have another bilge pump. And these saltwater pumps are fairly large. So you would take that bilge water and directly send it overboard. Now, just understanding with this, that if you were to do this, in other words, you would make sure that all your water is going overboard. You would open the emergency bilge suction and close your sea suction and use this pump, use one of these big main pumps to pump bilge water. You are going to pump any oil in the bilges directly over the site. So this would never be used unless it was an emergency.